What if SpaceX just solved the biggest weakness in Starship's heat shield? The one problem that could make or break its future Mars missions. Today, we're diving into the mystery of Starship Ship 38 and why engineers believe its new hex tile arrangement and attachment pin geometry could be the breakthrough that changes everything. From aerodynamic stress to tile bonding, this is the quiet evolution happening right now at Starbase. And by the end, you'll see why Ship 38 might be the most important Starship yet. Every Starship that's flown so far, from SN8's spectacular belly flop in 2020 to Ship 37's near-perfect re-entry, has been part of a learning curve unlike anything we've seen in rocketry. The biggest challenge? Surviving re-entry. At Mach 25, temperatures can exceed 1400 degrees Celsius across Starship's windward surface. That's hot enough to melt stainless steel. To survive that kind of thermal onslaught, SpaceX relies on a hexagonal heat shield system made of ceramic-based tiles, small, black, interlocking hexes that can absorb and deflect immense heat while maintaining structural integrity. But there's always been one major problem: tile loss. Even though the tiles look strong, they're surprisingly delicate. They're mounted using pins and studs that allow for slight flexing as the steel beneath expands during heating. Lose one tile, though, and the exposed area can cause cascading damage as hot plasma rips through the gap. That's exactly what engineers have been trying to prevent since Ship 20. Ship 20 introduced the first full heat shield layout. Ship 24 refined it with reinforced mounting rings and improved adhesives. Ship 28 began testing denser tile groupings and alternate gap fillers.
Now, Ship 38 is rumored to take that system one step further, not by replacing the tiles, but by re-engineering how they connect to the skin itself. Traditionally, each Starship tile is secured with 3 steel pins that fit into spring-loaded sockets welded to the hull. This creates a floating attachment that allows movement under heat expansion. However, the pins were aligned in a uniform triangular pattern, which, during high-speed descent, led to predictable stress concentrations at certain tile edges. Ship 38 is believed to introduce asymmetric pin geometry, meaning the pins are slightly offset rather than evenly spaced. This simple shift could distribute aerodynamic forces more evenly, preventing edge liftoff during re-entry buffeting. It sounds minor, but in hypersonic flight, minor changes can be revolutionary. At hypersonic speeds, airflow doesn't behave the way we imagine. It compresses, vibrates, and forms chaotic shock patterns. On a flat heat shield, the airflow curls over each tile seam, creating tiny vortices that tug at tile edges thousands of times per second. If all attachment points are perfectly symmetrical, those forces can align and amplify, prying the tile off like a bottle cap. By offsetting the pins slightly, even by a few millimeters, SpaceX can detune the resonance frequency, breaking that synchronization. The same principle is used in aircraft wing panels and stealth fighters. Don't let vibration frequencies stack up in phase. If Ship 38 proves that asymmetric pin spacing works, future Starships could carry lighter, thinner tiles without risk of blow-off, a massive win for performance and cost. At Starbase, photos of Ship 38's midsection show unusual tile groupings near the flaps and lower windward section, areas where airflow is most chaotic. Instead of perfect honeycomb uniformity, there are irregular seams, slightly angled and overlapped. Those irregular seams might indicate testing zones where SpaceX is evaluating how tile shape, spacing, and mounting respond under aerodynamic shear loads. When Starship re-enters Earth atmosphere belly first, it experiences multi-directional shear. The leading-edge tiles near the nose experience compression, while the aft tiles near the flaps experience suction and torsion. The aerodynamic load on each tile can exceed several kilonewtons per square meter, roughly the weight of a small car pressing on a single tile. If one pin fails or flexes too much, the tile doesn't simply fall off, it begins to flutter. At Mach 15, that flutter is fatal. It propagates heat and vibration to neighboring tiles, and within seconds, an entire section can fail. Ship 38 is built to prevent that. There's also speculation that Ship 38 uses revised bonding materials behind the tiles, possibly a flexible, high-temperature, silicone-based adhesive instead of rigid carbon epoxy. This layer acts like a shock absorber, dampening vibration energy.
Combined with the new pin geometry, SpaceX could achieve a system that's both thermally stable and mechanically forgiving, something no other spacecraft of this size has managed before. NASA's space shuttle faced similar problems. Tiles cracked, fell off, or shattered under vibration. But the shuttle had about 24,000 unique tiles. Starship's stainless steel frame and uniform hexes are simpler and easier to replace, as long as they stay attached. Simplify, standardize, iterate. That's SpaceX's design mantra. According to internal reports, Ship 38 might also carry embedded thermal sensors behind major tile sections to collect live heat flux data during descent. If those sensors confirm that asymmetric pin geometry reduces both vibration amplitude and localized heat flux, SpaceX will have a data goldmine. It would prove that Starship's system can handle re-entry at even higher velocities, possibly around Mach 30 on Mars return missions. Imagine a heat shield that's lighter, reusable, and survives multiple flights. That's what Ship 38 is testing. The big question is whether SpaceX plans to recover Ship 38 intact or let it burn up after data collection. If it returns and is inspected, we could see the first refurbished tile sections, a major step toward true reusability. Why does this matter so much? Because in rocketry, the smallest detail defines the biggest mission. A stronger, lighter attachment system means better mass margins. Better margins mean higher payload capacity. Higher payload capacity means cheaper access to orbit, and that means faster progress toward deep space missions. Every Starship improvement isn't just about power, it's about refining the details until the whole system works like clockwork. Falcon 9 became legendary because SpaceX mastered reusability down to the gasket. Starship will only succeed if it does the same for its heat shield. Ship 38 could be the one to prove it's possible. If Ship 38's data confirms improved thermal resilience, expect to see the same configuration in Ship 39 and Ship 40, the ones expected to carry payload bay doors and orbital refueling interfaces. Those flights will push Starship's design limits even further. Better tile retention also means faster reflight cycles, possibly cutting turnaround time from months to weeks. Imagine Starships launching multiple times a week like commercial planes. That's the future SpaceX is building, and it starts with the changes on Ship 38. Behind every upgrade are the engineers at Starbase, welding, mounting, testing, and refining tiles one by one. These are the people shaping the hardware that could one day land a reusable spacecraft on Mars. Ship 38 isn't just a prototype. It's a statement of persistence and iteration. If you love exploring how rockets evolve, hit the like button, subscribe, and share this with someone who follows Starship's journey. Here, we don't just watch launches, we uncover the engineering that makes them possible. The future of space isn't built in giant leaps. It's built one pin, one tile, one ship at a time. Stay tuned, because next time we'll dive into how SpaceX is modifying the Super Heavy booster's catch system for its most daring reusability test yet.